Take a clean image of a small world, a teal platform, a lime cube, a horizon line, and one light that knows exactly where its shadow belongs. Now add a little noise, then a little more. At first, the cube is still a cube, its edge softens. The shadow loses its job description. Eventually, the frame is almost pure static. If you stare at that static and see a face, congratulations. Your visual cortex has shipped an unreviewed generative model. The strange part is that a trained generative model can begin with that static and move back toward a coherent scene. It is not pulling a photograph out of a hidden filing cabinet. It is learning a controlled route through uncertainty. The route has a name in diffusion models. A clean example is called x0. A corrupted version at step t is x-soth. Epsilon is the random noise that made the corruption. A neural network with parameters theta learns to estimate what direction would undo some of that corruption. Often while looking at a condition C, such as a text prompt, when the model samples, it starts from noise and repeatedly applies the learned correction until a sample appears. That gives us the central argument for this episode. Generative models are not one machine with one universal trick. They are families of predictors. One system predicts pixels, another predicts a denoising direction in a compressed latent space. A transformer can predict token relationships. A flow model predicts a continuous velocity field. A world model predicts how a hidden state changes when an agent takes an action. The output may look similar, but the thing being predicted is different, and that difference determines what the system can control, what it forgets, and what it can plausibly simulate. We will derive the forward noising equation instead of waving at it, follow the reverse objective all the way to sampling, and then add the practical machinery, conditioning, guidance, latent spaces, DDPMs, and flow matching. After that, we will examine two very different systems. MiniMax H3 is documented as a multimodal generation system that jointly works with video and audio latents. Genie 3 is presented by Google DeepMind as an interactive world model that responds to actions and promptable events. Both can generate moving images. Only one of those descriptions is already making an action loop the center of the product story. Keep 7 variables on screen. X0 is clean data. X0 is a noisy state. Epsilon is noise. Theta is the learned predictor. C is the condition. S is a world state. A is an action. We will return to the same variables until the final distinction becomes almost annoyingly obvious. A generated video is not automatically a world model. There is a useful psychological trap here. Once the reconstruction looks intentional, it is tempting to imagine that the model understood the scene in the human sense. The equations do not grant that conclusion. A sample is evidence that a learned distribution can produce a coherent observation under a chosen condition. It is not by itself evidence that the system has a persistent object file for the cube, a causal theory of the lamp, or a plan for what happens if somebody pushes the platform. The random seed is also worth keeping visible. Two seeds can begin as different noise fields and still converge toward scenes that satisfy the same condition. The condition narrows the distribution. It does not delete randomness from the process. When an engineer changes the seed, guidance scale, sampler, or latent resolution, the result changes because the entire route through the distribution changes. This is why a production team should preserve the prompt, negative prompt model mode, seed, input frames, and source checksum beside a plate. The clip is the endpoint of a reproducible configuration, not an orphaned file that happens to look good in a review window. Our persistent cube is therefore doing two jobs. It is a visual object the viewer can track, and it is a reminder that representation is an engineering choice. In the forward process, the cube is deliberately destroyed by a known recipe. In the reverse process, a predictor tries to recover the statistics that make a cube likely. In a world model, the question would be different. Does the internal state preserve the cube's position, support, velocity, and response to an action? Same visible object, different predictive obligation. Before we derive diffusion, we need a family tree that does not confuse the fruit with the gardening equipment. A variational autoencoder, or VAE, learns an encoder and decoder around a latent representation. Its job is reconstruction with a probabilistic regularizer. Take an observation into a compact code, then decode a plausible observation back out. The latent is useful because it compresses, but a VAE by itself is not the same as a model that learns a long reverse trajectory from noise. A GAN puts a generator and discriminator into an adversarial game. The generator tries to make samples that the discriminator cannot distinguish from data. The useful mental label is not the model predicts noise. It is the model learns to fool a learned critic. Two networks argue, until one becomes a convincing liar, a completely normal workplace structure. This can produce sharp samples, but the game has its own instability and coverage trade-offs. An autoregressive model predicts the next token conditioned on previous tokens. For text, the tokens may be words or subwords. For images and video, they may be discrete codes or continuous patches arranged in a sequence. Its natural loop is one prediction after another. It can be wonderfully explicit about ordering, but long outputs mean many sequential decisions. Diffusion models take a different route. A forward process gradually corrupts data with noise. The learned reverse process predicts a denoising quantity at a chosen time. Sampling is a chain of updates. Flow matching is related in spirit but makes the continuous time object more explicit. Learn a vector field that says how a point should move through probability space. The model predicts velocity, not necessarily a list of discrete denoising steps. Then there's JPA-style prediction, where the target is a representation of a hidden observation rather than the hidden pixels themselves. The important word is representation. If the representation retains the information an agent needs, latent prediction can be a more compact planning substrate. If it throws away the object that matters, the system has achieved elegant amnesia. Finally, a world model adds an intervention question. Let S be the current state and A ho in action. The transition model predicts S ho pa approximately as F of S ho. And the model is useful when an agent can compare consequences of different actions, not merely admire a plausible continuation. This is a functional distinction, not a brand category. A video generator may be temporally coherent and still offer no reliable action interface. A world model may render observations, but its defining promise is state transition under intervention. So our family tree has one root question. What does the system predict? Pixels, a reconstruction code, a critic score, the next token, a denoising direction, a vector field, a hidden representation, or an action condition state. The rest of the episode is a tour through those answers. This comparison also explains why benchmark language can become slippery. Generation quality is not one scalar property shared by every family. A GAN can be judged by sample fidelity and coverage. An autoregressive model can be judged by likelihood and long context behavior. A diffusion model can be judged by perceptual quality, prompt alignment, and sampling cost. A world model needs tests that include interventions and consistency across rollouts. If we compare all of them with one screenshot, we are comparing the output surface while ignoring the machine. Underneath, the word latent is not a synonym for intelligent. A latent is simply a representation that the system uses internally. It can be compact, high-dimensional, continuous, discrete, spatial, temporal, or multimodal. Compression can remove nuisance variation, which is useful when the task does not need every detail. It can also remove the detail that becomes decisive at deployment. The right question is not whether a representation is latent. The right question is what information the objective rewards it for preserving. The word model is equally overloaded. A model can be a statistical map from input to output. A generator, a predictor, a simulator, or a component inside a larger agent. We will use world model in the narrow operational sense, a stateful predictive mechanism that supports counterfactual action consequences. That definition is intentionally less glamorous than saying the AI understands reality. It gives us something testable to draw on the slate. Now we build the part that looks almost too simple to power a modern image generator. Start with clean data x0. Choose a schedule of small positive numbers beta 1 through beta half. At each step, add a little Gaussian noise. The forward transition is written Q of xf given xf1 equals a normal distribution whose mean is square root of 1 minus beta t times xf1 and whose covariance is beta t times the identity matrix. In notation, Q of xf, the xo1 equals the square root of 1 minus beta ho x41 beta I, the identity matrix says. The independent coordinate directions receive the same variance in this basic formulation. Define alpha he equals 1 minus beta ho. Then one step can be sampled as x ho equals square root of alpha, x hal 1 plus square root of 1 minus alpha, where epsilon tho is standard Gaussian noise. The clean signal is slightly shrunk, and fresh noise is injected. The practical trick is that we do not need to run all earlier steps to manufacture a training example at time t. Define alpha bar t as the product of alpha 1 through alpha. If you substitute the one-step equation into itself, the signal multipliers multiply. The old noise terms are independent Gaussians. and a weighted sum of independent standard Gaussians is still Gaussian with variance, equal to the sum of squared weights. The result is the closed form, xo equals square root of alpha bar ho, xo plus square root of 1 minus alpha bar ho, epsilon with epsilon sampled from 0i. That equation is the visual spine of this chapter. Keep xo fixed on the left. Draw one fresh epsilon on the right. Let alpha bar slide from near 1 toward near 0. Early in the schedule, the clean signal dominates. Later, the noise term dominates. At the end, the model has a state that is close to a simple Gaussian prior. The forward process is not learned, it is our corruption recipe. Why use many small steps instead of one dramatic obliteration? The chain creates a family of intermediate states whose statistics are known. A model can practice denoising at every noise level. It sees the same object under a controlled progression rather than being asked to guess a complete photograph from an undifferentiated disaster. The schedule determines how much signal survives at each T, so the TEEP step is not decoration. It tells the network what kind of uncertainty it is looking at. Notice what has not happened. The system has not learned the meaning of a cat, or the laws of physics. We only chose a corruption path. Meaning enters later when a neural predictor is trained to reverse the statistics of that path using examples. Diffusion starts with destruction because destruction is easier to specify than creation. The laboratory recipe is, take something real, corrupt it in a known way, and ask a model to tell you how the corruption happened. The induction is worth making explicit because it is the part most often compressed into a single arrow. For one step, x1 is square root of alpha 1 x0 plus square root of 1 minus alpha 1. For two steps, substitute x1 into the second transition. The signal becomes square root alpha 2 square root of 1 x0, which is square root of alpha 1 alpha 2 pot x0. The first noise is also multiplied by square root of alpha 2, while the second noise enters with square root of 1 minus alpha 2. Because the two noise draws are independent standard Gaussians, their weighted sum is a Gaussian whose variance is alpha 2 1 minus alpha 1 plus 1 minus alpha 2. That simplifies to 1 minus alpha 1 alpha 2. Repeat the argument and the product becomes alpha bar t. This is why alpha bar is a useful production variable. It tells us the total signal retention without forcing the viewer to memorize every individual beta. A shot can keep x0 and epsilon fixed, move a single alpha bar slider, and show the state changing in a way that is mathematically faithful to the closed form. At late t, the image has the information density of a group chat after 2 in the morning. The viewer sees the same clean geometry and the same random draw, not a different image at every stage. That persistence is not merely aesthetic, it preserves the causal story of the equation. The schedule also controls where the learning problem is difficult. At low noise, the predictor must recover small details without erasing edges. At high noise, it must infer global structure from weak evidence. The intermediate range asks for both. A schedule with too much signal loss too early can make the reverse problem unnecessarily ambiguous. A schedule with too little corruption may not expose the model to the broad uncertainty it must handle at sampling time. The paper supplies the formal process. Implementations choose schedules and parameterizations around that process. There is a final distinction between data corruption and semantic editing. The forward process does not know that the cube is important. It corrupts every coordinate according to the schedule. Any later preference for cubes, faces, or landscapes comes from the training distribution, the conditioning signal, and the learned reverse predictor. Noise is neutral at the corruption stage. Meaning is introduced by the data and the model that learns to reverse it. Now read the implementation panel from the equation outward. Epsilon is one random tensor with the same shape as x0. Alpha bar at t is one scalar selected from the schedule. The first code line scales the clean tensor by square root alpha bar. The second scales the noise tensor by square root 1 minus alpha bar. Addition produces x. The function returns both xt and epsilon because training needs the noisy input and the exact corruption target. 4 lines of code do not replace the derivation. They prove that every symbol has an operational job. The forward chain is fixed. The reverse chain is where learning happens. If the data distribution has been gently blurred by a known Gaussian step, there is a corresponding reverse time distribution. In the original denoising diffusion formulation, the reverse transition is modeled by a neural network whose parameters depend on the current noisy state and the TEEP step. We can write a simplified predictor as epsilon theta of x of t and c. It receives the noisy state, the noise level, and optionally a condition such as text. The common training target is the exact noise epsilon that we use to synthesize x-soft sample, a real x-soft sample at TEEP step t. Sample standard Gaussian epsilon, construct x who with the closed form. Then minimize the squared error between the known epsilon and the network's estimate. L equals e of x minus epsilon theta of x who t c. This is a wonderfully economical teaching signal. The model does not need a human to label the left side of the cube became uncertain. We know the corruption noise because we made it. If the predictor learns to estimate that noise, it has learned a direction back toward the data manifold under the schedule we chose. It is not finding the original cube so much as composing the statistically least embarrassing apology. The TEEP step embedding matters because the same pixel pattern can mean different things at different noise levels. A faint edge at early t may be a real edge with mild corruption. A similar faint edge at late t may be a coincidence inside almost pure noise. The model gets a representation of t, often a sinusoidal or learned embedding, and injects it into the network blocks so every layer knows the current denoising regime. A text condition can enter through cross-attention or another conditioning path. The network is not handed a sentence and asked to be creative in one step. It is asked, repeatedly, how the current noisy state should change while respecting that condition. There is a score intuition underneath. The score is the gradient of the log density with respect to the state. It points toward regions where the data distribution is more likely. For Gaussian corruption, the optimal noise estimate is related to that score by a scale factor. You can think of epsilon theta as a coordinate-friendly way of predicting the local correction, while score language describes the same neighborhood as a density gradient. The episode will keep the distinction honest. The network is trained with a noise prediction loss, and the score is an interpretation of what that prediction encodes. At sampling time, start with XUF at the final noise level. Ask the network for epsilon theta. Use the schedule and the model's estimate to compute a less noisy state, X felt 1. Repeat, some samplers retain stochasticity. Others use deterministic or ODE-like paths. The important loop is not mystical. Estimate the corruption, apply a mathematically specified update, and carry the new state into the next TEEPS test. The model therefore learns a local rule, but the sample is produced by composing that rule many times. This is why one bad direction early can echo through the rest of the chain. It is also why visual quality depends on both the predictor and the numerical schedule. The neural network supplies learned information. The sampler decides how that information is integrated. One is an approximation to a reverse statistical process. The other is the route we take through it. The reverse distribution can be written more precisely as a Gaussian, whose parameters depend on the current state and TEEP step. In the original formulation, the variance and mean parameterization can be related to the posterior of the forward process. The simplified objective used in practice focuses the model on predicting the noise, which gives a stable regression target and a convenient route to the reverse mean. We do not need to show every variational bound term to understand the operational loop, but we should not pretend the simple loss is the entire derivation of the probabilistic model. The predictor's error has two scales. At one TEEP step, an error means the proposed correction is slightly misaligned. Across many DeepMs, those small errors can alter composition, identity, or texture. The sampler therefore exposes a numerical stability problem as well as a representation problem. A network that estimates noise well under one schedule is not automatically optimal under every schedule. A sampler with more updates is not automatically better if the predictor is being asked to extrapolate beyond the regime. Where it learned reliable directions conditions complicate the reverse distribution, because a prompt can be compatible with many images. A red cube on a teal platform is a set of possibilities, not a single target. The reverse process must choose one sample while keeping enough diversity for the prompt to remain a distribution. Guidance can narrow that set, and a seed selects one route through it. The output is therefore neither a deterministic database lookup nor unconstrained improvisation. It is a learned stochastic procedure whose randomness is progressively shaped by the model. This also clarifies why a denoiser can look like a renderer without being a renderer in the traditional graphic sense. It is not tracing the exact light paths of a known scene graph. It is estimating a direction in a learned data distribution. The generated image can be physically convincing because the training data contains regularities about lighting, perspective, object boundaries, and texture. Convincing appearance and explicit causal state are separate achievements. The reverse code panel separates training from sampling. During training, predicted is epsilon theta of x, t, t, and c. The loss compares that tensor with epsilon squares each difference and averages. Backpropagation changes theta. It does not directly change xt. During sampling, theta is frozen. The sampler reads the model's estimate and computes a new state. So L names the scalar objective, E means average over many random training draws, and the squared norm says large component errors receive a larger penalty. The same predictor participates in two loops, but only one loop updates the model. A model can learn to denoise without text, but a useful generator usually needs a steering signal. The condition C might be a caption, an image, a class label, a depth map, an edge map, a first frame, or another latent. The condition does not replace the noisy state. It changes which reverse directions are considered plausible. Text-to-image systems often use cross-attention. One stream represents the noisy visual tokens. Another represents the text tokens. Attention creates links between them. A word such as lime cube can influence the visual features that decide shape and color, while long shadow can influence geometry and lighting. This is not a guarantee that every word receives a pixel-perfect appointment. It is a learned coupling between condition tokens and denoising features. Classifier-free guidance is a particularly clear steering trick. During training, the model sometimes sees a condition and sometimes sees the condition removed. At sampling time, call the model in both modes. Let epsilon con be the prediction with the prompt, and epsilon uncon the prediction without it. Then combine them as epsilon guided equals epsilon unconned plus W epsilon minus epsilon unconned. The guidance scale W amplifies the direction that points from the unconditional sample toward the conditional one. At W equal to 1, the conditional difference is used what? At larger values, prompt alignment is emphasized. This can make a requested object more obvious, but it can also overcook textures, collapse diversity, or produce brittle anatomy. At guidance 40, Tung Tung Tsuhur is apparently God, the cube has abs, and every surface is screaming 8K. That sentence is deliberate generated nonsense, not theology. The mechanism is the point. The model can become intensely obedient and visibly wrong. The slider is not a truth meter. It is a trade-off between condition adherence and the model's broader data, supported distribution. Negative prompts are best described as another conditioning convention, not as a magic list of forbidden concepts. Depending on the system, the negative text changes the conditioning path or the unconditional reference. The exact behavior is model and implementation dependent. In our diagram, the negative prompt enters the steering lane and receives an editorial warning badge whenever the model's documentation does not specify the mechanism. The sampler schedule adds a second kind of steering. DDM-style updates can follow a more deterministic path under a chosen schedule. OD intuition describes the continuous limit. The state travels along a learned vector field and a numerical solver chooses the stepping. Flow matching makes that vector field language primary. Different schedules and solvers can reach different points because a learned predictor is approximate and the path is discretized. That is why prompts are not specifications in the engineering sense. A prompt influences a probability path. The sampler, guidance scale, seed, latent representation, and model prior all participate. Stronger steering can increase semantic alignment while reducing natural variation. More steps can help until the numerical and model errors dominate. The generated image is the final state of a controlled experiment, not a signed contract from the network. A condition can be strong or weak for different parts of the sample. Text may strongly constrain a named object while leaving the exact background open. A first frame may anchor identity but leave future motion ambiguous. An edge map can constrain contours without telling the model which material or lighting setup produced them. The conditioning path is therefore a channel with finite influence, not a direct command line into every latent coordinate. The guidance formula is easiest to misunderstand when its scale is treated as an aesthetic knob with no statistical meaning. The unconditional prediction provides a baseline direction. The conditional prediction provides a direction informed by C. Their difference is the model's estimate of how the condition changes the denoising field at that state. Multiplying that difference changes the trajectory. It does not add new information that was absent from both predictions. If the condition is ambiguous or the model has weak coverage, higher scale can amplify the wrong distinction. Seeds are useful for comparisons because they hold one source of randomness fixed, while a prompt or guidance setting changes. But a seed is not a universal identity lock. Change the model, latent size, conditioning encoder, or sampler, and the same integer may describe a different initial field or a different trajectory. A first frame or first last frame control can provide stronger continuity evidence, but it still needs visual review. The production plate plan treats continuity as a test, not a promise. The guidance code makes the limitation visible. Unconned is the baseline estimate. Conned is the estimate with C. Their subtraction is a direction, delta epsilon, multiplying by W changes. Only the length of that direction. It does not query a new database, add a missing fact, or verify the prompt. If both predictions misunderstand the scene, guidance can amplify the misunderstanding with tremendous confidence. That is why the Sahur plate belongs here. It is the comic visual endpoint of a perfectly ordinary vector operation pushed beyond useful judgment. Pixels are an expensive place to do every calculation. A high-resolution frame contains spatial detail that the model may not need at full precision during every denoising update. Latent diffusion inserts an autoencoder around the process. The encoder maps a frame or short sequence into a compressed latent Z. Diffusion operates in Z-space. The decoder maps the final latent back to pixels. This is not simply throwing information away. The autoencoder is trained to preserve a useful perceptual reconstruction, and the latent space is chosen so the generative model spends capacity on larger structure, instead of resolving every local pixel relationship at every step. But compression creates a contract. If identity, fine text, or a tiny object matters, the latent and decoder must preserve it well enough. A fast latent model can be confidently wrong in a space the viewer cannot inspect. Video adds a third axis and a new set of failure modes. A frame can look excellent while the object changes identity between frames. A camera can drift, motion can freeze, melt, or invent a new joint. Every frame may be gorgeous while the protagonist changes grandparents between cuts. Long horizons accumulate small errors until the scene forgets its own geometry. The model must coordinate appearance, motion, temporal causality, and conditioning. A useful shot plan, therefore, tests first frame continuity, first-last frame transitions, and stress cases rather than trusting one attractive clip. DiT makes the backbone itself more transparent as a token processor. In the DET paper, a latent is divided into patches and processed by a transformer. The model gets step and conditioning information, transforms the token sequence, and predicts the diffusion quantity for the latent. The important conceptual move is not that transformers are magic. It is that scaling the token processing backbone becomes an explicit design axis. More compute can buy a stronger predictor if the data, objective, and sampling setup support it. Flow matching changes the picture from a stack of denoising decisions to a learned continuous velocity field. Let x0 be a source point and x1 a data point along a chosen probability path. A vector field v theta xt predicts the velocity needed at time t. An ODE solver integrates dx dt equals v theta xt from source to data. Conditional flow matching trains the field by regressing toward velocities from known paths, without requiring the training loop to simulate the final ODE. Diffusion and flow are not synonyms, and the episode will not collapse them into one marketing bucket. They can share continuous time ideas and sampling intuitions, but the predicted object and training construction differ. Calling every model that emits moving pixels diffusion is architecture astrology with a GPU. In both cases, the engineering question is the same. How much compute is spent predicting the next correction, and how much state remains coherent as the sample gets longer? For video, the answer is not only a better frame score. It is identity persistence, motion plausibility, temporal memory, and a way to preserve condition alignment over many updates. A video generator can be judged by the clip it renders. A world model must additionally be judged by whether its state remains useful after an action changes the scene. In a video, latent tokens can carry more than one kind of neighborhood. Some relationships are spatial, pixels or patches near each other in a frame. Some are temporal, the same object at adjacent frames. Some are conditional, the prompt, a reference image, or an action signal. A model can flatten all of these into a sequence, factor them into blocks, or use attention to connect them. The implementation choice changes compute and inductive bias. But the production question remains visible. Does the same object survive the transition? The autoencoder also changes where errors become visible. A latent may preserve broad composition while weakening small text. A decoder may smooth a boundary that was precise in the latent. For a technical explainer, that is exactly why factual labels must remain vector-authored. A generated plate can supply atmosphere and motion. It should not be responsible for rendering the equation that the viewer must read. Flow matching provides another useful vocabulary for video because a continuous field can be integrated with different numerical budgets. But a smooth mathematical path does not guarantee smooth semantic identity. The learned field still reflects its data and conditioning. Long rollout quality depends on how the system handles information that should persist, and on how it handles uncertainty that should branch rather than collapse into one confident continuation. In the flow snippet, x is the current point on the probability path, v theta is the learned velocity at x and time t, and dt is the solver's step size. One Euler's step adds d times velocity to x. A practical solver can use better numerical rules, but this tiny line exposes the contract. The network predicts velocity, and the solver performs integration. The decoder appears only after a latent state is ready to inspect. Smooth code execution still does not certify that the same face, hand, or cube survives semantically. Numerical continuity and identity continuity are different tests. Now we move from general machinery to a named system, and the first rule is to read the documentation at the level it actually supports. MiniMax's official H3 materials describe a family of components rather than a single slogan. The repository names H3 Context IR, H3 Base, and H3 Regenerate 2K. The base system is described with visual and audio VAEs, an H3 encoder, and an H3 Omni transformer. The documented picture is multimodal. Video and audio are represented as latents, and the 33 billion parameter dense transformer is described as jointly predicting video and audio latents. That makes H3 interesting in our family tree. The system is not best explained as a text prompt goes into a classic image DDPM and a video comes out. The official materials expose a multimodal latent pipeline in several generation modes, including text-to-video, image-to-video, and first-last frame controlled video. The repository also documents short generation settings and CFG distilled checkpoints. These are published system capabilities. They are not the same thing as a complete public derivation of the exact training objective. So the architecture plate keeps our language disciplined. On the left, a prompt and optional frame conditions enter an H3 encoder. In the middle, video and audio latent streams meet the Omni transformer. On the right, separate decoders produce the visual and audio artifacts. Then a large evidence boundary says, exact objective unresolved in the sources used for this episode. We can describe the inputs, the latent representations, the joint prediction claim, and the output family. We should not invent a diffusion versus flow label for the checkpoint simply because that label would make the family tree look tidy. The distinction matters because system descriptions travel faster than training details. A multimodal transformer that predicts latents may borrow ideas from diffusion, flow matching, autoregression, or a hybrid objective. The name of the visible product does not settle the mathematics. Otherwise, the architecture diagram becomes a horoscope with arrows. Our claim ledger therefore marks H3's architecture facts as vendor reported, cites the repository and announcement, and marks the not simply another diffusion model line as editorial inference. For the production, the factual H3 architecture stays entirely deterministic. Optional moving B-roll comes from the locally installed 4-bit LTX 2.5 derivative instead, because this is where motion behavior, not H3 internals, is the subject. We use it for reconstruction texture, first frame continuity, first and last frame control, temporal drift, and the appearance versus state transition. Every such clip is labeled synthetic plate LTX 2.5. It demonstrates one reviewed output under one configuration. It does not become evidence about H3 or Genie. That boundary is deliberately boring and therefore useful. Equations, component names, source URLs, model specifications, and the H3 data path remain Vector Meridian graphics. The generated plate supplies motion and atmosphere. The source supplies the claim. The narrator owns the mix, and the local plate remains silent. The H3 reading also gives us a model of responsible vendor documentation. First, list the name components exactly as the source names them. Then separate the data path from the product claim. The data path in the repository includes encoders, VAEs, an omni-transformer, and decoders. The product claim includes supported generation modes and release checkpoints. Finally, record what the source does not establish. In this case, the materials we reviewed do not justify a detailed sentence about whether H3's core objective should be classified as a conventional diffusion loss, a flow matching loss, an autoregressive latent loss, or a hybrid. That missing detail is not a failure of the episode. It is a useful example of evidence boundaries. Scientific communication becomes less reliable when every unknown is filled with the closest familiar architecture name. The viewer deserves to know which layer is documented and which layer is inference. On the architecture plate, source badges attached to the documented nodes. The unresolved objective boundary is a different visual object with a quiet warning color and no invented equation. The local LTX package is a 4-bit MLX derivative with group size 64. On this 24GB machine, the two-stage path previously stalled under heavy memory pressure, while the one-stage low RAM path completed a 25-frame 512 by 288 candidate with 6 denoising steps. That is a successful local render, not a universal hardware benchmark. Each candidate stays short, then loops or holds in the edit only after the output passes identity, flicker, and provenance review. This is also why a plate does not silently become commercial approved. The visual file can be technically complete while its checkpoint terms runner license or generated output terms remain unreviewed. Provenance is attached at ingest, checksum is calculated, and review status stays draft until a human examines the plate. If a clip becomes useful in the edit can point to the reviewed asset. If the clip fails a continuity test, the deterministic scene still works without it. The plate prompts are intentionally abstract. They ask for a geometric cube, controlled grain, or a state transition without asking the generator to typeset a formula. Generated text is one of the easiest ways to turn a beautiful clip into a factual error. The final equation is drawn by the same deterministic renderer as every other piece of source-bearing typography in the episode. Genie 3 changes the center of gravity from make me a clip to let me act inside a generated environment. Google DeepMind presents it as an interactive world model. The announcement describes text-prompted environments, user interaction, and promptable events. It reports 720p output at 24 frames per second for a few minutes. Those numbers are useful, but the more important architectural idea is the loop. Let S be the current world state. Let A be in action, move forward, turn, jump, push, or choose some other supported interaction. The transition model predicts a next state, S101 approximately FS up. The approximation sign is doing honest work. A learned world model is not a physics engine with perfect hidden variables. It is a predictor whose state may include visual memory, geometry, agent context, and whatever internal representation the training system made useful. A renderer turns the predicted state into an observation. The agent acts again. The model rolls forward again. If the state does not preserve the information needed for the next consequence, the world can look stable while its hidden logic is quietly dissolving. If I press left and the moon becomes a horse, that is not simulation. That is Tuesday on the internet. That is the difference between a video continuation and an interactive model. In a continuation task, the condition can be a prompt and a preceding frame sequence. The system is judged on plausible appearance and temporal coherence. In an action loop, the next output depends on an explicit intervention. The viewer or agent can test whether a bridge remains where it was after turning around, whether an object responds consistently to a push, and whether an event can be induced rather than merely displayed once. The official Genie 3 description is also clear about limitations. The announcement discusses a few-minute interaction horizon, a constrained action space, limitations in multi-agent interaction, and visual details that can fail. We will show those limitations as a boundary around the world, not hide them behind a beautiful fly-through. A world model is useful precisely where it maintains a predictive state under interventions. A polished render alone cannot certify that property. For the visual transition, the H3 plate ends as a decoded multimodal artifact. The slate folds that artifact into a state variable SHO. A lime action arrow HO enters. The next state is rendered, then the camera returns to the same landmark so the viewer can compare it. That repeated landmark is not scraped demo footage. It is an original Vector Meridian diagram illustrating the action loop described by the official materials. Genie 3 therefore occupies a different branch from a pure rendering system. It still generates observation. But its defining claim is not only that an image sequence looks plausible, it is that an agent can inhabit a generated environment long enough to train, test, or reason through consequences. The limits tell us how far that claim currently reaches. Few minutes is not an eternal world. 24 frames per second is not guaranteed physical truth. Promptable events are not the same as open-ended agency. Good scientific communication keeps the loop and the boundary on the same screen. The symbol S is intentionally less specific than a rendered frame. It stands for whatever state the model maintains that lets the next prediction depend on history and action. That could include visible geometry, hidden memory, object identity, agent pose, or other learned variables. We should not draw an internal tensor and label its coordinates the true physics unless the source establishes that interpretation. Our diagram uses a state node because the action loop is the claim under discussion, not because we know the exact hidden representation. The loop creates tests that a one-off video does not. Turn the camera away from a landmark and back. Apply an action that should alter one object while leaving another alone. Trigger an event and see whether the environment remains coherent after it. Roll out several steps and measure where the prediction begins to drift. Even when a system passes some of these tests, the result is a bounded capability under a particular interface, data distribution, and horizon. It is not a universal guarantee that every imagined intervention is physically meaningful. The official numbers belong on the same evidence rail as the limitations. 24 frames per second describes a reported temporal output rate. 720 pixel resolution describes a reported visual setting. A few minutes describes a reported interaction horizon. None of those quantities alone establishes a stable latent state, a complete action space, or open-ended multi-agent simulation. Keeping the numbers and caveats adjacent prevents a specification from becoming a superpower by typography. That is why the Genie transition is an original diagram rather than scraped demonstration footage. A demo clip can be illustrative, but its provenance, editing, and hidden interaction history may be unclear. Our plate only carries the structural idea from one generated observation to a state node, an action arrow, and a next observation. The source citations carry the factual claims. The diagram carries the explanatory relationship. The world loop code is intentionally almost boring. Transition receives state and action, then returns next state. The decoder turns next state into a frame the agent can observe. The assignment of next state back into state is where persistence enters the loop. If that assignment carries useful memory, a later action can depend on an earlier consequence. If it carries only a pretty frame with no durable structure, the interface may still generate video while failing the stronger simulation test. F is the learned transition. The approximation sign admits prediction error. And AT is not decoration. It is the intervention that lets us ask a counterfactual question. We can now sort the futures without sorting them into winners. The first future is rendering appearances. Predict pixels or pixel-adjacent latents well enough to make an image, a clip, or a multimodal artifact. Diffusion, latent diffusion, DiTs, flow models, and systems such as H3 live in this broad generative territory, even when their internal objectives differ. The second future is representing hidden state. Encode the parts of an observation that a later task needs. Predict those representations, and keep the state compact enough to plan over. A latent can be a shortcut, but it is also a responsibility. Whatever the representation drops may be impossible to recover later. The third future is simulating consequences. Maintain a state S-hook, accept an action A-hook, predict S-hook, render enough of that state to inspect it, and repeat. This is the world model ambition. It asks for temporal consistency, memory, intervention, and a useful boundary around uncertainty. The same generated frame can appear in all three futures. That is why screenshots and demos are not enough to identify the machine. Ask what was predicted, what was conditioned, what can be changed, what persists, and what the documentation actually establishes. Then trace the claim to a source. A generated video is not automatically a world model. A video generator can make a door explode beautifully. A world model should remember there used to be a door. It becomes part of a world model story only when the action loop, persistent state, and limitations are real parts of the system rather than captions we added after the render. These branches can also coexist in one product. A generator may decode a beautiful observation from a compact latent. A representation learner may provide a state for a planner. A world model may render its predicted state so a human can inspect the consequence. The categories describe the dominant prediction target, not a law that forbids hybrid systems. The practical habit is to ask 5 questions whenever a new demo arrives. What is the input condition? What is the model trained to predict? What state or memory persists between outputs? Can an external action change the next prediction? What limitations were tested or disclosed? The answers tell us more than the phrase world model, video model, or multimodal model by itself. The visual closes on the same cube from the opening. In the render branch, it is an appearance. In the representation branch, it is a compact code with a continuity obligation. In the simulation branch, it is part of a state that must respond to an action. 1 cube, 3 predictive responsibilities. That is the whole episode in one frame.